So then this is about the chapter 4, which is the elastic deformation of axially loaded member. Again, in our learning objective, you read the elastic deformation. So this is the, my lecture note about that. So elastic deformation. If we have a uniform cross-section, so then we can think about this kind of bar. So this can be like a rectangular shape or a circular shape, but we have a constant cross-section area and length L. And what is E? What is E? Modulus elasticity. That's correct. Young's modulus is correct. You did the test in the lab, right? Yes. So then E is material property. So if we have a rubber, if we have a steel, which one is larger? E. Larger E. Are you sure, guys? Again, modulus of elasticity, larger E. Jen is correct. Larger E, when we have a rigid or stiff member, we have a larger E. So Young's modulus is material property to measure the stiffness. Okay, so steel is stiffer than rubber. That's why the steel has a larger E. Okay, so this is ALE. Then we apply the load. And now in this case it's pulled, and the other end is fixed, right? So then obviously this bar will elongate because we deal with now the deformable body rather than rigid body. So my question is two things. One is what is stress in the cross section? Second is what is the deformation delta? Can we calculate? So that is the main problem of this chapter. So the first thing is because we have, I wrote this as a P, but the N is a symbol for the normal axial load. So then if we have this P, then sigma, which is stress caused by this P, can be calculated from our chapter 1 discussion, right? So then cross section is A, this is area, so then sigma is equal to P over A. This is called axial stress formula. Again, you're gonna learn 4 types of formulae. Axial stress formula, shear stress formula, bending stress formula, and torsional stress formula, right? So then you're gonna learn those 4 formulae, then this is one of them. And because sigma is a normal stress causes normal strain, which is epsilon, right? And what was the definition of the epsilon? Epsilon was deformed length divided by original length, L, right? So this is epsilon. So then these two we learned in chapter 1 and chapter 2, right? And in chapter 3, we learned these relations. Sigma is E epsilon, right? And E is a Young's modulus. So now what we're gonna do, we're gonna use these three equations to calculate the elastic deformation, which is delta, right? So then we plug P over A here and delta over L here, right? Then we want to solve for the delta, okay, as a result of this P. So then delta can be calculated as this. Delta is equal to PL over EA. Very important. So when I put a green box, that means important. So delta is equal to P. P is axial load, which is external force. L is original length of the bar divided by E is Young's modulus, and A is a cross-sectional area. And E is a material property, right, of the bar. A is a shape property, okay? So okay, we have questions here. So then Jenny asks, can we do a problem involving this? Yes, definitely, we will do that. And Gabriel, will we be given the Young's modulus for the problem? It depends on for example, if I ask you to calculate delta, which is deformation, the elongation, then I have to give you what is E, right? But I can ask that, okay, as a design problem, I want to limit this delta a certain value for given P and L and A, and what is your choice of the material? And you want to determine E, right? So that is depends on. George asked, what is a little E stand for again? This one, E, this one? Epsilon? Yeah, yes, yeah, this is epsilon. Epsilon is, again, in chapter 2, strain, right? And by shape, you mean the cross-section, right? Definitely, Victoria. That you actually asked the very important point. When I say the shape, that is a cross-section mostly, okay? But we have, in this formula, we have one more shape related, which is L, right? L is also shape related. So interestingly, if we use again, E is a stiffness, right? So then if we have a stiffer material and it has a bigger resistance, you can think about steel and rubber example, right? Rubber, if we have a steel which is a large E, we're gonna have a small deformation, elongation, right? If we have a big cross-section area, then we have small elongation. If we have a large force, definitely this is proportional to that. And if you think about the short bar and very large bar, and then you apply the same force, larger bar will elongate more. This is what this formula says. Any question up to this point? And very important thing relate to the design. So you want to control this deformation. So then you don't want to have a very large deformation when you design a building, right? So then you want to, control this not to have like excessive deformation. Then for given PNL, then you have two choices for the design. One is material choice. Second is shape choice, okay? So when you design, you always play with your material and shape. Very, very important. And then this will keep, coming up. And one of the very important reasons why we learn this class is you want to design your structural, structures, right? So then basically when you design, you are playing with these two parameters, material and shape. We will get to that later with the examples. Now, the previous one was a simple one, so then cross-section is a constant. But this one shows that elastic deformation axial loaded member, but we have now the non-uniform cross-section, right? So the cross-section is function of x. And material can be also function of x, right? Which means that depending on different location of x, your material can be stiffer or smoother, okay? But the same thing, we have a sigma is P over A, but now these two are the function of x. So then d delta is equal to px over ax ex. Then what we have to do, we have to take an integral from the 0 to L, right? So this is what we do. And if the material is uniform in x, then ex becomes a constant. So then E can be constant value, so that it can be out of the this integral. So then we have this equation for variable cross section.